Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm glad that Grigori gave this talk this morning because he and I and many other people, some of whom are listed here and some appear actually in the reference Grigori was giving, have been working since 2003 in what we call the Rewriting Logic Semantics project, where so the main goal is to see how well and how completely we can use rewriting logic and a number of tools, formal tools for execution and model checking and verification to define and analyze programming language definitions and programs in those definitions. And today I want to focus on just one particular strand of work within that, which is work on definitions of real-time programming languages and the specific issues that appear there. So the general idea, of course, is that given a language, there is a substantial gap between formal semantics for the language, implementations, and analysis tools. And one of the important goals of the Rewriting Logic Semantics project is to narrow that gap. And again, Grigori did part of the work for me this morning, explaining the idea that we want everything to be semantics-based. So that the implementations and the analysis should directly be based on the semantics of the language. And I will focus on the scalability issues for real-time programming languages and also modeling languages, because we have been giving semantics not only to programming languages, but also to software modeling languages and to hardware definition languages. So, the approach is that the formal semantics of a language is given as an executable rewrite theory, and then is used as the basis for language implementations and for program analysis. And as I said, we can also do the same thing for software modeling languages and for hardware description languages. And in particular, we also have been giving semantics in this way to a number of real-time programming languages and also modeling languages for embedded systems. In general, this approach has been proved to be expressive using the Maude implementation of rewriting logic and also tools built on top of that, like the K tool, and quite efficient and scalable. But real-time languages pose particular challenging issues, which are the ones I will be focusing on after giving a little bit of an overview. Just in a nutshell, in just a single slide, what rewriting logic is a logic where to specify concurrent systems. And the concurrent systems are specified in a rewrite theory. A concurrent system is specified as the model defined by a rewrite theory where sigma is a signature defining syntax and types. Then E is a set of equations. Sigma and E, therefore, is just an equational theory. And then R is, so that describes what I call the statics. Defines for you what are the states of your system. And then the dynamics are described by rewrite rules that define local concurrent transitions that can happen in the system. And of course, the rewriting happens modulo the equations because the states are elements of this algebraic data type defined by the signature and the equations. Maude is a rewrite engine capable of executing these specifications, but also provides formal analysis techniques with several tools, including several model checkers. Maude is just a language executing these specifications, has execution for what are called functional modules, which are equational theories, which are assumed to be confluent and terminating equations E modulo axioms like associativity, commutativity, identity, and so on. So the rewriting happens modulo these axioms. And then rewrite theories add an additional component, which are the rewrite rules that describe the local transitions. And under certain simple executability conditions, like confluence and termination for the equations, and what is called coherence between the rules and the equations, which is a commutativity property, then all these things can be efficiently and completely executed, completely in the sense that the execution is complete, covers all the behaviors. And then there is a whole formal environment with several model checkers, including a linear temporal logic model checker, several tools to analyze confluence, termination, coherence, inductive theorem prover, a tool to didactically prove invariance, and so on, in which you can reason about these specifications. And then, so given a language L, semantics is a rewrite theory, so where the syntax and also the state, components of your configuration are defined as an algebraic data type, then the deterministic features are defined by equations. So you have a language that is sequential, then you probably can do everything just with equations because there is a deterministic thing. So either the program terminates with a value or it loops forever. But for concurrent features, then rewrite rules are the thing to do because they support concurrency and can be highly non-deterministic. And then both Maude and the formal analysis tools can be used to define a language, and then also the K-Maude tool and the K-definitions can also then use Maude, as Grigori was explaining, as the engine in which then these definitions are translated into a rewrite theory. And this scales up to realistic languages. So Grigori and Asade Farsan and Fencheng and I years ago did Java and the JVM, the Scheme, C, Verilog. Large languages have been done this way. Another important thing is that both a rewrite theory has both an operational semantics by rewriting, but also a denotational semantics and initial model semantics, and both coincide in the sense that under this confluence and coherence conditions and so on, there is a perfect identity between the operational and the denotational semantics, and so the denotational semantics can be used as a basis for inductive reasoning principles and for correctness of reasoning on the specification. There is also the distinction between rules and equations is very useful and very important because it provides a language specifier with what you might call an abstraction dial. So you have always the option of make everything into rules. So then, it's sort of the most concrete possible specification of your language. But you can also identify what aspects of your language are deterministic and then use those with equations. Of course, the key point is that equations should be confluent, and also, of course, they should also be coherent with the rules. And so this gives you a more abstract semantics. This is enormously useful for model checking because for model checking concurrent programs, you don't care really very much about what is happening in some deterministic subcomputation inside a thread. You care about what happens in the interactions between such threads. And so then you have much fewer states for model checking. This gives you a tremendous state space reduction just by the possibility within the logic of choosing between deterministic aspects done with equations and concurring and possibly non-deterministic aspects done with rules. As also Grigori was pointing about, so abstract semantics is just a special case in which your values, instead of being concrete values, they may be abstract values like types and so on. But essentially the same approach gives you also an abstract semantics. And Mark Hills, and years ago, developed a whole C pluggable policy framework for abstract semantics like this. People at Technical University of Valencia have used an abstract semantics of Java based on the Java semantics that we developed to reason about security of Java programs and non-interference. And Chucky Ellison also developed techniques to define type systems in K. So abstract semantics in some way becomes a special case of concrete semantics. So written logic is a logical framework, so it doesn't really take sides in the particular definitional style. So in some sense, it's kind of an ecumenical framework in which many different styles are possible, small step or bigger step or modular structural operational semantics, as Peter Moses proposed, or chemical abstract machine or continuation-based semantics. All these styles can be faithfully represented. This is work that Servanuta, Grigori, and I published a little while ago, in a step by step. So there's a lot of flexibility for accommodating different styles or defining new styles. And the logic as such doesn't take sides, although, of course, certain particular choices may be more efficient, may have certain advantages. And we are certainly interested in modularity. So, the K framework, MSOS, and so on have, good modularity features. So the general philosophy is to define a programming language as a rewrite theory, then to use tools like Maude or K to execute these definitions, test them, to experiment with new extensions of a language and so on, and then use the abstract semantics to do a static analysis, and then use generic, and the key point is generic, formal tools, like a model checker for rewriting logic or other such tools to analyze your programs. And then use matching logic and reachability logic, as Grigori was, again, as a generic approach to do deductive verification. So since this is a workshop on scalability, I included a slide with my view of some aspects of scalability that I think are coming up in the discussions, and I want to kind of also bring. So one that Peter Moses actually was talking about in his talk this morning was in some way related to the idea of modularity and reusability. So for large languages, you would like these definitions, and Egon Berger also was talking about that in a different way. So you want these things to be understandable and reusable, and there are several approaches. MSOS approach of Peter, then Cristiano Braga and I show how within rewrite logic MSOS could also naturally be expressed, and then K framework of Grigori using the idea that you are rewriting modulo associativity and commutativity with these notions of cells and so on, has also achieved highly modular definitions, highly modular and reducible definitions. And there is another aspect that is scalable executable definitions. So when Grigori was looking, he showed this comparison of different C semantics. One of them used a functional language, but factorial of 6 wouldn't terminate. So that's not very scalable. And so you want to be able to have large languages and have this 99.2% of cases being tested because the things can actually run. So that's certainly a dimension of scalability that you care about to be able to validate the definitions. But another part that is also important is scalability of program analysis. So model checking, theorem proving, static analysis tools, can we also make them as scalable as possible? And generally speaking, in these 3 dimensions of scalability, the experience has been quite positive, but as I am about to tell you, in the case of real-time languages, it's a little more challenging, and there are some more specific issues that I want to get to. So let me just move on to, yes?
So one aspect of scalability or modularity.
Shall I go back?
Sure.
Yeah.
Is whether the extension preserves the old semantics. So suppose you're specifying a theory and then you extend it to the new aspects, say timing or whatever.
Yeah.
You want the old semantics to remain intact. Has there been any work on, say, K or Maude in general regarding conservativeness?
Well, so to begin with, just having modular definitions already is a big step in that direction, because then when you are adding new things, you don't have to change any of the previous. So the question, the most interesting work I have seen on that direction is by Peter Moses in the form of meta-theorems. So meta-theorems where you want to prove that, well, if I use this feature, say, one example I think that Peter has done is sequential composition is going to be associative. And you want that to be irrespective of what other things you are adding. So first of all, you want to be modular, and second, you want to have as much as possible meta-theorems of that kind that ensure that good properties will not be lost because you will have this conservative extension.
I should just point out, Jose, that that work was together with Mohammed.
Okay. So then, I'm preaching to the choir, right? I mean, I'm telling you about your own work, right? Sorry about that.
No, I'm sure he's quite happy to hear.
Yeah. Maybe I was set up to, to advertise you a little bit.
The question was whether there are similar results in K, for example, or in Maude in general about conservatism.
Well, Maude is a language, so Maude itself, it would be in the writing logic, right? So I don't think we have looked as deeply into this direction as you have, but I think it would be very natural and appropriate to do so. Yes. Going back to semantics of real-time languages. So the question is, how do you deal with real time within the writing logic? And it's quite simple. You just need to have a data type of time. And this data type can be discrete or can be continuous. You can have several choices on that. And then you have to describe the state of your system. Now it's going to have what you might call the normal discrete state of it. Discrete or continuous. I mean, you could have timers that have continuous time, right? I mean, so the state in their normal sense of the word, together with the global clock. And so that their state really is the pair of the state of everything in your system together with the time, right? And essentially then the discipline is to have two kinds of rewrite rules. Rewrite rules that are 0 time, so that they happen instantaneously and don't change the time. And then rewrite rules, and which may be local, and rewrite rules that are global, that move the entire state of the system and describe the passage of time, just by the simple passing of time. Say, for example, timers are going to decrease and things like that. So they are described by what we call tick rules that advance the time of the system, okay? And so therefore they are just, a special style of rewrite theories that, have time as one of the data types and describe how things change over time or instantaneously.
Can one execute a tick rule together with instantaneous rules simultaneously, so to speak?
Well, so typically, the good thing will be that, tick rules will advance typically until the next time when something becomes enabled. Like maybe a timer becomes 0. And then a whole bunch of 0 time rules will happen until nothing else can happen at that time. And then tick rules and 0 time rules will kind of
So it's
alternate.
Between, so to speak, the system without time and the timing.
Right, the advancement of time. So and then all kinds of changes happen instantaneously, but when something becomes enabled. Using these real-time rewrite theories, we have been given we or other collaborators have been given semantics to, well, one of my former students, Mustafa Turki, worked with in the Docomo labs in Palo Alto, and they had a language that internally they call L to model, concurrent real-time protocols and systems, and the whole semantics of this language to design, new systems was given in the writing logic. It was just there to prototype and analyze these things, and also could model check, these designs, and had also an abstract semantics that, could also be used. My former student Camilo Rocha and Cesar Muñoz, a researcher at NASA, have for several years worked on giving semantics to a language called Plexil, of which I will have more to say, which is heavily used as NASA to program robots in automatic missions, in unmanned missions and so on in vehicles, and is now used heavily inside NASA as the standard. So when they found problems with the Plexil implementation and so on, and new extensions on the language are first done by extending the semantics and then doing analysis and so on. And I'll come back to that because Camilo Rocha has contributed one of the important new methods to achieve greater scalability. So I'll revisit Plexil a little bit later. Mustafa Turki and I gave semantics to Misra's ORC language, which is a real-time process calculus, and developed both an SOS semantics and a more efficient reduction semantics for it, and a model checker, and even using the semantic definition, also a distributed implementation of it. And people in Oslo have been also working with the time Creole language, object-oriented language, again using these ideas. And all these programs can be simulated and model check in Maude or in the real-time Maude, real-time extension of it. In a similar way, we have been looking at several languages for modeling languages for embedded systems, and in particular at Ptolemy 2, which is a modeling language at University of Berkeley, developed by Edward Lee and people in his group, and heavily used in industry, and also AADL, which is an industry standard used in Airbus and Boeing and different such companies for embedded systems. So Peter Olbesky and my student Kyung-Min Bai and I have worked on giving semantics to these languages, and then using that semantics directly as an execution environment and model checking environment for them. And similar work has been done by other researchers in the emotions modeling framework and the Moment 2 modeling framework at the University of Leicester here in the UK. So let me just tell you briefly about Ptolemy 2. Maybe I can show you a picture. So this is a Ptolemy 2 model of a traffic light. And so it's based on the idea of actors that send messages to other actors. And the actors themselves are, when you click, are these abstract state machines. So there, the semantics in rewriting logic is that blue button over there, which generates the formal semantics for this model in real-time Maude, and then you can actually give formulas to model check about this. And in fact, the fact that the traffic light in this case was had a problem sort of showed up in the model checking of it. This is just one of the rewrite rules in the semantics, which is a tick rule that avances time, for the Ptolemy 2 models. In a similar way, the semantics of a subset of AADL has been defined in Maude, and we have identified a synchronous subset, of which I also will have more to say a little bit later, because it's another very useful technique to reach greater scalability. And so this AADL2 has a tool called Osate, built on top of Eclipse, where you can define all these models And then it again has a plugin using real-time Maude where you can execute the models and also you can model check them. And I'll come back to that later because this is also a place where a new technique to achieve scalability has been developed. This is an example of an AADL model of an automatic pilot with two sides and the environment and the pilot also giving commands of an active standby that I will revisit precisely later on that. And again, this is a tick rule for the semantics, so in rewriting logic for the advancement of time in models of AADL. So here are the scalability. Here is, I said at the beginning that in the case of real-time languages, there are particular challenges to scalability, and particularly to scalability of analysis. If you want to do model checking analysis, for example, there are a number of new things that you have to deal with. The first thing you have to deal with is that the tick rules are non-deterministic. So how much you advance time is in general open. So R prime could be chosen to be different values from time R to time R prime. But more importantly, what is really challenging is the combined effect of concurrency and the non-deterministic interaction with an open environment. So many of the applications you're going to program are cyber-physical systems that involve sensors and actuators. And these sensors have to read values, the program has to read values provided by the sensors, which from the point of view of the program are non-deterministic. You don't know what the sensor is going to give you. And that, together with the fact that your system often will have to be distributed, the combined effect of the external non-determinism from the environment plus the concurrency makes the analysis, especially the model checking analysis, very challenging. Furthermore, the external environment, the non-determinism there can be even infinitary. Maybe it could be, an infinite number of possible values that the thing could take. So how to deal with these issues is non-trivial, and that's in some way the thing I want to kind of focus on. But just to kind of get a little closer to that, you could ask a very simple question, which is, how is the fact that the distributed real-time system is open, that is, interacts with a non-deterministic environment model? How is this model actually concretely in the rewriting logic framework? And the answer is very simple. It's modeled by rewrite rules where there are extra variables on the right-hand side. A normal rewrite rule, even though, of course, is the rules are non-deterministic in the sense that many different rules could be applied, and then depending on which one you applied, you might reach different states, so there's the non-determinism of that. But the typical rules, however, if you match the variables x on the left-hand side, then what the right-hand side will be is uniquely determined. But if you have extra variables, then it's not, because then any substitution to those extra variables is one possible outcome. And so what is happening really with openness in an open system is that, for example, these variables y could be values of sensors that are being read, and then depending on what they are, then maybe you will do different things. So this is concretely how the rewrite rules model that situation. And of course, executing these rewrite rules is now more challenging than executing normal rules because, how do you deal with these extra variables y? Yes?
So what are your conventions about when you are allowed to apply such a rule, and when a tick rule, and when a state transforming rule?
Well, so tick rules are an example of this, because the y in this case would be the time you're advancing. But more importantly, we have ways to deal with those, so these are not so problematic. Because one of the things that you can do, and under very mild conditions, this is a complete strategy, you can advance the time, like in discrete event simulation, to the next instant when something becomes enabled.
Yeah, because it's here that you typically will have to decide about what kind of sampling you have, no? I mean, how often you read from environment, what are the new values of sensors and so on.
Right, right. So tick rules are, are non-deterministic like this, but easier to handle. Easier to handle because, you can typically just tick until something becomes enabled, and this is when you would have to do something, right? But the rules that describe interaction with non-deterministic environment are more challenging. And if furthermore your system is concurrent, then you have, huge amounts of non-determinism. One given by the concurrency and another one given by this kind of choice of the, what happens with the external environment. There are two techniques that I want to describe that we have been developing to deal with these, particularly more challenging issues that, apply particularly to real-time language definitions of languages that support concurrency, because many of the real-time systems we have to deal with are distributed real-time systems. And also with interaction with an external environment, which also typically for any cyber-physical system is going to be what you need to do. So these techniques are, one, the technique of rewriting modulo SNT. So you rewrite by modulo decidable theories. And the other one is the technique called pulse that reduces a virtually synchronous distributed real-time system, like say distributed control systems are a good example of that, to a much simpler bisimilar synchronous one. And this achieves enormous state space reduction, as I will show you a little bit later. And I'll explain both, beginning with SNT, rewriting modulo SNT, and how this can be used, and then particularly how it can be used to deal with this external environment. And then I will then explain pulse. So the work on rewriting modulo SNT is the PhD thesis work of Camilo Rocha, who is now teaching at the, who has worked on this, Plexil semantics at NASA, and is now working at the engineering school in Bogota, Colombia. So, so the idea is you have a rewrite theory where a subtheory of it is the theory of some decidable data types, like, Peano arithmetic, Pressburger arithmetic, or bit vectors, or, rational numbers, or things like that. So this is given by subtheory sigma 0 E0, and then the rest of the equations are just only axioms for the rest of the data types, like associativity, commutativity, and so on. And this subtheory is protected in the sense that new operators will not go into those sorts. And then the rewrite rules that you can define are rewrite rules, of the form t rewrites to t prime, where these variables y can have sorts in the source at 0 corresponding to the decidable types. Okay, so the new values having to do by, that come from the environment will be values in these decidable data types for which, you have an SNT solver. And this can be conditional to a condition which can be any quantifier-free formula on sigma 0, which is the subsignature for the decidable theory. By doing variable abstraction, you can very easily reduce it to a canonical form in which all the subterms in the decidable type are variables, because you can abstract them as variables. So if you had, say, an arithmetic expression, you just can put it in the constraint part and then just reduce it to that. And so then matching now with this becomes very easy because, when you're matching on the data part, you just match with variables, which are all different. So this is just a syntactic transformation. And then the key idea is the idea of rewriting now pairs of terms whose only variables are variables in the decidable type, and formulas which are constraints. So, and conceptually, what this pair tells you is all the instances where you instantiate those variables by data in the decidable type are states acceptable, provided for those instances the formula phi is satisfiable. So that's the set of states described. So now a single term, a single pair like that defines an infinite set of possible states. And then there is a rewriting, modulo SNT relation, which essentially matches a rewrite rule with U, replaces by T prime where the variables are all fresh variables for the new Y's, and then essentially conjoins psi with the substitution instance for the matching for the condition of the rewrite rule. And there is a lifting lemma that tells you that any concrete rewriting that you could do with this can be lifted, is covered, so that this is a complete way of covering what in fact would be an infinite number of concrete rewritings for each instance of the Y's that you could achieve. So in particular, this semantics, so in the Plexil work, as I told you, for several years, this has been heavily used at NASA, but before developing this rewriting modulo SNT, since they had to deal with the interaction with the external environment, what they needed to do was to assume that there would be certain values in the internal environment, and then do the analysis of the execution relative to that. This is now what has become unnecessary, and a complete execution can be achieved because you can assume any values for the external environment using constraints, and this form of rewriting modulo SNT. So this language has been used in Mars drill, in the International Space Station, in habitat demonstration, and there are all kinds of big applications within NASA that are using this language, which is a distributed language, real time, and dealing with an external environment of sensors, in which tasks of different robots solving problems in a NASA space mission and can be programmed. So Plexil itself is a deterministic language, but the external environment is not. So it's deterministic. Once you know what the values of the sensors are, then what Plexil does is determine. But of course, those values are non-deterministic. Using Maude extended with CVC3 and CVC3 oracle to solve SMT constraints, then a full symbolic verification of safety properties for Plexil programs, and also a symbolic execution of the programs, for arbitrary environment inputs has been made possible. Let me just give you a very simple example, extremely simple, but this illustrates the point. So this is a Plexil program where you have two threads and have a shared variable x. One assigns 1 to it, and another one assigns 2 to it, but they do a lookup on the environment. So there is a sensor S, and then if the value of the sensor is greater or equal than 0, then one loop will do that, and the other one, if it is less or equal than 0, will do the other. The rewriting logic semantics modulo SNT has the beauty that all the executions in Maude, including the model checker, the LTL model checker, can be used exactly as before. So you can do all the analysis that you were doing before, but now on these symbolic terms. And so in particular, if you want to model check from the initial state with the with the constraint true for the, remember that the states now are pairs of a term and a formula, and you want to see whether the program is race free, then you get the answer false, because of course the value 0, is something where one thread could do one thing and the other one thread could do the other. But instead, if you want to see that from the initial state in which s is greater or equal than 1, then it is race-free for that case. So this is kind of, again, a very simple example, but gives you the idea of the kind of analysis that you can do in dealing with this non-determinism due to the external environment. So let me move on to PALs. So many cyber-physical systems are distributed and correspond to a collection of components that communicate asynchronously, typically through a network. So something like in an airplane, for example. And they are going to have local clocks, and they have to change a state and respond to the environment within a hard real-time bound. And typically, they are distributed and asynchronous, but they have to achieve some kind of virtual synchrony, because all the components have to do something within a certain period. This is just typical of distributed control, for example. So integrated model avionics, distributed control in motor vehicles, certain interoperations of medical devices are examples like that. And these things are often safety critical, but they are very hard to design and verify and implement because there are problems due to asynchronous communication, race conditions, message delays, clock skews, and brute force development of these things is enormously costly. And furthermore, at the end of the day, since many of these systems have to be certified and they are high assurance, you don't even know whether they actually work properly or not. In dealing with the semantics of these real-time languages, and in particular of AADL, we experience huge, enormous state space explosion because of this concurrency and also interaction with an external environment. So this clearly is something beyond what you would get in a normal programming language, and which requires techniques like the one of PALs and the one, those two techniques together are the way to deal with it. So let me explain to you what PALs is. So it stands for physically asynchronous, logically synchronous transformation. So where you reduce the very difficult issue of designing a distributed real-time system that should work as if it were synchronous, in which there is a network and clock skews and so on around, to the much simpler task of designing a synchronous system in which all these complexities disappear. And then it's a transformation where you produce from the synchronous design an asynchronous one which is correct by construction under certain assumptions on the underlying network, the clock skews, and the execution times. We developed it with researchers at Rockwell Collins and colleagues at University of Illinois, but then Peter Ovesky and I developed a formal semantics and a proof of correctness for this transformation, first in a conference and then last year in theoretical computer science in a journal paper. So this is what it is. You begin with E is a synchronous design, and I will make clear what that is in a moment. And gamma are performance bounds on what it's like a contract. So assuming that the implementation has certain bounds, then we can guarantee for you a correct asynchronous implementation of it, correct by construction. So the performance bounds are the maximum clock skew of the clock synchronization algorithm, the minimum and maximum time for reading input, performing transition, and producing output for each component, and also the minimum and maximum message submission delays, that can be guaranteed by the underlying network. And then E gamma is the corresponding asynchronous design as a collection of objects that communicate my message passing that is correct by construction. So a synchronous model is a very simple thing, is a collection of state machines that work in lockstep. So the output wires are wires from the environment, the input wires are inputs from the environment, the output wires are wires to the environment, so it's like sensors and effectors. And then each machine can receive inputs from other machines, including itself, and from the environment, with the assumption that whatever a machine outputs will become input only in the next time, okay? So there's a intrinsic 1 unit delay on when outputs from one machine become inputs to itself or to other machines.
So this is the maximum time of all the input readings by all the components plus all the times they may need for internal interaction.
Yeah, so the constants, so this is of course not here because this is just the synchronous design, yeah. But the constants are, you know, the maximum clock skew, the maximum time that it takes for a message to arrive from one node to another, and then also the maximum time that it takes for each component, which will correspond to one of these machines, to perform a transition, read inputs, perform a transition, and generate output. So those are the constants that are the inputs to the transformation. And then the distributive implementation essentially adds a wrapper around each machine. It has an input buffer and an output buffer, okay? And then it has 2 timers, a round timer that tells you the period and a back-off timer that tells you when is the right moment to send the outputs to the other components. Yeah, and the behavior of each node is that, you know, it reads messages from the input buffer, executes the local transition, generates new message, but doesn't send them yet, puts them into the back-off, into the buffer, and then when the back-off timer expires, then that's the moment when it sends it to the rest of the components, and then, you know, the cycle repeats. Yes.
Crucial, you mentioned this, but was it crucial that the time it takes a message from being sent and being received from the sender, that this is also part of your...
Yes, because that determines the period. So we have a result that the period, which is computed, the period of the asynchronous system is computed, you know, by taking into account, you know, the maximum time for network communication plus the times, plus the clock skews, plus the execution times, of course, and, you know, so all those has to be taken to determine the smallest possible period where this can work correctly. So that if you produce a period smaller than that, there are no guarantee that you will be correct. But any period that achieves that bound or more will be correct. So in order to achieve actual synchrony, when you have message passing communication, there's no free lunch. You cannot achieve that, you know, in 0 time, right? So you need some time.
Yeah, this I see, but I was wondering because I've seen systems where the message passing, so to speak, was not considered as so crucial, whereas the reading and data from sensors,
yeah,
that was crucial. So it would go into all your...
Yeah, all this is taken into account. Yes. So the key theorem is that you can identify, as you were saying before in your own talk, not all states are meaningful in relation to the other one. So because here you will have a state in the distributed system where things are piecemeal. Some things have advanced, other things have not advanced. So we identify a class of distributed states that we call stable, that are states that correspond to synchronous states. And the key theorem is that, you know, the system, or more precisely the Kripke structure of stable states and the Kripke structure of the synchronous system are bisimilar. And as a corollary, they satisfy exactly the same temporal logic formulas. So for purposes of verification, we can verify the much simpler synchronous system and be sure that the asynchronous, much more complex asynchronous system, which is impossible to model check, will be correct if the synchronous one is correct. Okay, so that's the advantage. And so just to illustrate, let me come back to this standby model, you know, that I showed you in AADL, and what that means, what this transformation means there, is the synchronous model has only 185 states and can model check in 0.2 of a second. The asynchronous model, in the simplest possible case in which there are no delays, has 3 million states. And if you assume that there could be either a 1 unit delay or none, then, after hours, you just run out of memory. So this is a, huge drastic state space reduction. And this is a simple example. We have done something much more challenging, like, for example, a whole airplane with the turning maneuvers, and also what we call multi-rate pulse, where different components can be functioning at different rates. So in this case, there were controls in the wings and in the tail, and then a central control and a pilot. And then we specified, the whole control of the turning maneuvers of an airplane. And using multi-rate pulse, we were able to model check, the entire, turning maneuvers of an airplane. If we had the asynchronous version of it, would have been totally impossible. This is a much more, much bigger example than this one that we had done more recently. So to conclude, I have told you first about the rewriting logic semantic project, to give semantic definitions, and that what we're trying to do is, of course, as many of you are trying to do in other ways, is to close the gap between theory and practice by supporting executable semantic definitions that scale up to real modeling languages, programming languages, and hardware languages, as Verilog, for example. And then using tools like Maude and Kmod, we can, directly use these definitions to obtain interpreters, model checkers, theory improvers, static analyzers. And I have been focusing on scalability of distributed real-time language definitions, which is more challenging for the reasons that I have told you. But I have presented to you 2 techniques that we have found very useful to deal with those particular issues that appear in the case of real-time languages, namely rewriting modulo SNT and the pulse transformation. And we have already experienced with these techniques, in the case of the Plexil language at NASA, and also in the case of the AADL, what we call the synchronous AADL sublanguage of AADL, modeling language, in which we can, apply this pulse transformation to deal with the much simpler synchronous models and verify those. And what we haven't done yet is to develop a generic infrastructure, because of course what you want is to combine these 2 techniques. For example, if you go back to this picture here, there are environment inputs, like the site 1 failed, the site 2 failed, so failures that can happen from the environment. And here we didn't use the SNT, but the environment was small enough that we could just do a normal model checking. As soon as you start adding more environment inputs, and they are not just Boolean values, but numbers or something, this would just blow up. So the pulse transformation alone would not do it. So what you want is to do the pulse transformation together with rewriting modulo SNT. And they're perfectly combinable. There's no, as I said, rewriting modulo SNT combines perfectly well with normal model checking. So in this case, we were just lucky that we have a small enough environment. But otherwise, this wouldn't, just pulse alone wouldn't do it. So what we really want to do is to combine both techniques. There's no problem in combining them, but at the moment we're just in the process of developing the whole infrastructure where these things can be used not only for Plexil and for AADL, but for other real-time languages. And so that's in some way our near-term future work. Thank you very much for your attention, and I'll be happy to answer questions and discuss things with you on these ideas. Thank you.